I want to give you a little support with the Dalton's law of partial pressures and talk about the challenge problem level 4 today in class. Many of us didn't get to this, so I want to address it because it's going to come back up again for our lab today. Or not today, but this week on Friday. So problems like these are called collecting a gas over water. And it's a very common technique to collect a gas over water in lots of different scenarios. Mainly because we can control where the gas is going to go, bubbling it through water and then into a collection vessel. So this is a very old school common technique that's used in lab. So the scenario that you were given in level 4 and the one you see in your textbook is heating up a solid sample of this chemical called potassium chlorate. It's KClO3. So it's a solid here. You'd heat this with a Bunsen burner. It would decompose, this is a decomposition reaction, to form two products, KCl, which is a salt, and oxygen gas. So we get one gas in our product. So as you see here in the little cartoon I drew, the gas would start bubbling or flowing through the tube here. It would go into our collection vessel. There's water here. Okay, this is the water part. And the gas bubbles up, and as more and more gas comes, the water level is going to get pushed down. This is called water displacement. So when it does this, it doesn't just bubble up and it's all O2 up here. You actually get some water vapor that's carried up into this collection area. So your sample, although you think it's all oxygen, there's going to be some water vapor molecules in there. And we have to account for that in this problem. So that's what I'm going to really show you. So it says oxygen gas is produced by the decomposition of KClO3. We know that already. What is the partial pressure? This is what I'm looking for. This is what I want to solve for. What's the partial pressure of oxygen? I'll do it for both torr units and ATM so you can see both. If the volume of the gas collected is 0.20 liters, remember that's that sample up here, that's the gas. This is something that I'm going to be wanting to think about later. Temperature is also given, so I got volume, I got temperature. I have a total pressure of the gas, or P total. So that, remember, is again oxygen and water vapor, and it's in torr. And that's the first question. So what's the partial pressure of oxygen if the total pressure is that, the volume is that, and the temperature is that? So we'll deal with that first, and then we'll come back to the second question. Actually, I have to keep reading a little bit. So it says water has a vapor pressure of 25 torr at 26 degrees Celsius. This is the key piece of information to deal with the water that's in my sample. If I don't know the vapor pressure of water at the temperature that I'm dealing with, I can't account for it. So this is what you should recognize at this point. We have two things in the collection vessel, oxygen gas and water vapor. So P total is actually equal to P oxygen, or the partial pressure of oxygen, and the partial pressure of water. I know what P total is, right? There it is, 765 torr. I don't know what P oxygen is, but I do know what P water vapor is. And I can look this up in a table. They have tons of tables with the vapor pressures of water at various temperatures. So just all you need to know really is the temperature of your water. So we have a vapor pressure here of 25 torr. So now it's pretty simple to see how we can figure out the answer to the question of what's the vapor pressure sorry, not the vapor pressure, but the partial pressure of oxygen in our sample here. So we just do a little subtraction, right? So we do 765 torr minus 25 torr, and we get P oxygen equal to what is that, 730? Let me just double check my math real quick. Mr. Graham, you're not doing math well in your head. 740 torr. Okay, so there's your answer to the problem of what's the partial pressure of oxygen, 740 torr. If you want it in ATM, it's pretty simple conversion. 740 torr, dimensional analysis, here it comes. 760 torr is equivalent to 1 ATM. So we're going to be a little less than 1 ATM here. 740 divided by 760 gives us 0.974 ATM. So there's your answer for what level 4 is asking for you to do. Now, I put in another question here. How many moles of oxygen gas are produced? That's something we'll have to figure out in our lab. So we just figured out the partial pressure of oxygen. I'm going to use that now in ATM to answer this question of how many moles of oxygen gas are produced. Okay, so I know pressure of oxygen is 0.974 ATM. My volume, let's go back to the problem. There's my volume. My gas volume is equal to 0.2 liters. My temperature is 26 degrees Celsius. I'm going to convert that to Kelvin right now because I can't use Celsius. That should be something that you automatically do. And we get 299 Kelvin. And I'm looking for moles. So take a look at what you have, guys. Look at what you're looking for. If you haven't immediately thought of what equation to use, this is where you should be asking yourself, okay, here's the information I have, here's what I'm looking for, what equation do I use? And hopefully you recognize it's the ideal gas law. Okay? PV equals nRT. So, 0.974 ATM is my P. I'm going to multiply it by my volume. I'm going to set that equal to N and R. R is 0.0821 liters ATM mole Kelvin. And then my temperature, 299 K. So I'm going to solve for N. I'm going to divide both sides by R and T. I'm not going to write it out here, guys. And we should get sorry for the pause, 0.00794 moles of O2. Put it in scientific notation. Not very many. 7.94 times 10 to the minus third moles. So there you go, guys. I know it's challenging sometimes to figure out exactly what to do when you're given a problem with all this information, right? The key to this one was understanding that water vapor is going to be in our sample, and we got to subtract that out. We don't care about the water vapor. We just want to care about the gas of interest. From this problem, it was oxygen. So we subtracted away the vapor pressure of water from our total pressure. We got our pressure, our partial pressure of oxygen, and from there we could figure out moles. Hope that helps.